For hundreds of thousands of years, they were the undisputed masters of the frozen world. They weathered repeated ice ages, retreating and expanding in rhythm with the advancing glaciers. And then, quite suddenly, they were gone. To understand what it took to bring down a woolly mammoth, you have to look at the sheer scale of the animal. Standing up to 11 feet tall and weighing 6 tons, they were heavily armored against the cold and required immense amounts of daily calories just to maintain their body heat. They fueled that bulk by grazing on the mammoth steppe. This was a vast, cold and dry biome, the largest on Earth at the time. It formed a highly productive, continuous belt of grass and willow shrubs that stretched uninterrupted from the Iberian Peninsula in Spain, across Eurasia, over the Bering Land Bridge, and deep into Canada. A population that spans 3 continents for millennia is remarkably resilient. Their abrupt disappearance suggests a convergence of forces that overwhelmed their biological capacity to adapt. The critical window opens around 11,000 years ago, at the close of the Pleistocene epoch. Within a geological blink of an eye, the mammoth, along with about 70 other species of large-bodied mammals, vanished from the mainland. This massive die-off aligns with 2 major ecological disruptions. The global climate was undergoing a rapid, violent warming phase, and simultaneously, early modern humans were expanding deeply into the New World. Understanding why these giants vanished involves weighing 3 distinct factors: shifting environmental conditions, expanding human populations, and a possible novel pathogen. As the last glacial maximum ended, global temperatures spiked. Massive continental ice sheets began to melt and collapse, releasing fresh water to shift global weather patterns. The once arid, firm ground of the Mammoth steppe received a massive increase in precipitation. High-protein grasses were replaced by deep winter snows, and as the ground thawed, it transformed into expansive bogs and mossy forests that the heavy grazers could not navigate. The mammoth's endless pasture fractured. Instead of a continuous global range, the remaining herds were pinned into shrinking, isolated pockets of suitable vegetation. This looks like a complete environmental collapse, but there is a problem with the timeline. Ice core records show that mammoths had already survived several previous interglacial warming cycles that were just as severe. The melting ice destroyed their primary food supply and decimated their members. But history indicates that a retreating habitat alone should not have driven a resilient species to total extinction. If the weather didn't finish the job, the focus turns to human impact. In the 1960s, paleoecologist Paul S. Martin proposed the overkill model, arguing that highly coordinated human hunters systematically decimated the massive, slow-breeding herbivores. Recent mathematical modeling supports this theory's lethal potential. Running thousands of ecological simulations, researchers found that if human populations grew at a modest rate, hunters would only need to kill 1 mammoth every 3 years to push an already stressed regional population into irreversible decline. The mathematics of overkill are highly convincing on paper, but archaeologists quickly point out a discrepancy in the physical record. We simply cannot find the kill sites. Despite centuries of excavation and thousands of mammoth bones cataloged in North America, there are barely a dozen verified examples of stone projectile points actually embedded in mammoth remains. We are left with a frustrating contradiction. The demographic models show that human predation is biologically devastating, yet the ground yields very few physical signs of mass slaughter. To bridge this gap, a third theory suggests migrating humans, or the dogs traveling with them, introduced a novel pathogen to an immunologically naive continent, but the biological constraints on this potential pathogen are extreme. To cause this specific extinction pattern, a virus would need a mortality rate of up to 75%. It would have to transmit effortlessly across entirely different animal clades, while somehow leaving human carriers unharmed. No known pathogen fits that profile. Without empirical evidence in the bone record, disease remains a fringe theory, forcing us back to the intersecting pressures of weather and hunting. The mammoth's final stage on Earth didn't occur on the mainland. When rising sea levels severed a high spot of land in the Arctic Ocean, a small herd was trapped on what is now Wrangel Island, completely isolated from mainland predators. Out of human reach, these mammoths didn't perish at the end of the Pleistocene. They persisted for thousands of years, surviving all the way down to 1650 BC. They were still grazing in the Arctic while the Great Pyramids of Giza were standing in Egypt. Their final end was quiet. DNA analysis shows they weren't wiped out by a sudden freeze or a hunting party. They succumbed to the slow, compounding weight of inbreeding and genetic mutation that occurs when a species is confined to a tiny, isolated gene pool. Wrangell Allen demonstrates that the mammoth's biology was capable of enduring a warmer Holocene climate. They didn't fail to adapt. They simply ran out of physical space to maneuver. By overlaying climate data with the archaeological record, modern researchers have moved away from looking for a single cause for the extinction. The changing weather decimated their food supply and backed the remaining herds into isolated, fragile corners of the globe. Once their populations were fragmented and stressed, human hunting provided the final pressure, picking off the survivors faster than they could reproduce. It is a sober reminder of how extinction actually operates. A dominant species is rarely destroyed in a single dramatic event. Instead, it is slowly cornered by a changing environment until one final, localized pressure pushes it over the edge.